In sections 1.5 and 1.6, we're going to look at problem solving. There are 4 types of problems we should be able to identify. The first type is a one-step translation problem. These are typically simple word problems where we just have one arithmetic operation that we need to perform in order to solve it. The second type of problem is a multi-step translation problem. This here is where we need to take 2 or more arithmetic operations to solve our problem. The third type of problem are puzzle problems. Puzzle problems are typically a little different. They might cause you to use an unusual approach, draw a picture, try out different possibilities. They are typically considered non-routine and help students develop flexible thinking. The fourth type of problem are open-ended problems. These problems here ask for students to find more than one answer or use more than one technique to find their answer. With open-ended problems, typically students have a variety of answers that can be given. Section 1.5 takes a look at George Polya's 4 steps in problem solving. Step 1 is to understand the problem. Typically we ask students to read through the problem and try to determine what it is that you're trying to figure out. We ask them to look for the information that's important. A lot of time we have them circle the information that's important, and then if there's anything that's not needed, to cross it out. After students understand the problem, they need to devise a plan. Think about what strategy you're going to use. Are you going to be able to just do some arithmetic? Do you need to draw a picture? Do you need some trial and error? Are you going to be creating lists? And then also decide, is this something you can figure out with pencil and paper? Do you need a calculator? Can you do it in your head? Step 3 is once you devise that plan, carry out the plan. Show all your steps and explain your reasoning. And then the final step, step 4, is looking back. In looking back, you want to check your work. Check to see, does your answer make sense? And then possibly make up a similar problem to see if it can be solved the same way. In sections 1.6, we're looking at different problem-solving strategies. They list out several. We can use inductive reasoning to solve problems, and remember, inductive reasoning is looking at patterns. Look at several examples, and from those examples, try to come up with a conclusion. We can use logical or deductive reasoning. We can look at facts and put those facts together to deduce our answer. We can try guessing and checking. We can make a list or table. We could draw a picture. We can solve a simpler problem. We could work backwards, use a graph, use an equation, or take a break and try again. What we're going to do is we're going to take a look at a problem from the textbook on page 52, number 16. It is a pizza problem, and it looks at a pizza restaurant offering 10 toppings for its cheese and tomato pizza. The toppings are mushrooms, peppers, pepperoni, sausage, onion, anchovies, broccoli, black olives, banana peppers, and pineapple. And we want to look at how many different kinds of pizzas can be made by varying the combinations. So you could have a pizza that just has one of those toppings on it. You could have a combination of 2, 3, 4, all the way up to 10 different toppings on it. A plain pizza would be just a cheese and tomato pizza. It seems like a daunting task to try to determine what 10 topping combinations would look like. So what we're going to do to solve this problem is we're going to look at trying to solve a simpler problem and then see if we notice any patterns and maybe use some inductive reasoning to help us with that. So the first thing we're going to do is we're going to look at pizzas with just 2 toppings. And if our 2 toppings were, let's say, mushrooms and peppers, how many pizzas would we come up with? If those are our 2 toppings, we can look at having a plain pizza. We could have just a mushroom pizza. We could have just a pepper pizza, or we could have a mushroom and pepper pizza. This here would give us a total of 4 possible pizzas. If we then look at having 3 possible toppings, and this time our toppings are going to be mushroom, peppers, and onions. Again, we could have a plain. We could have a mushroom pizza. We could have a pepper pizza, or we could have an onion pizza. We could have a pizza that has 2 toppings. We could have a mushroom pepper or a mushroom onion pizza, or we could have a pepper onion pizza, or we could have a pizza that has all 3 toppings on it. We have 1, 2, 3, 4, 5, 6, 7, 8 different possibilities. So with 3 toppings, we have a total of 8 possibilities. Let's look at one more simpler example, and that would be if we had 4 toppings that we were looking at. So this time, let's say our 4 toppings here are going to be mushroom, peppers, onions, and broccoli. So once again, we can have plain. We could have just mushroom, we could have just peppers, just onion, just broccoli. We could have a mushroom pepper, a mushroom onion, a mushroom broccoli. We could have a pepper onion, a pepper broccoli. We could also have an onion broccoli. Moving on to 3 toppings, we could have a mushroom pepper onion. We could have a mushroom pepper broccoli. We could have a mushroom onion broccoli. We could have a pepper onion broccoli pizza, and then we could have a pizza that has all 4 toppings on there. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 toppings here. We can continue going on, but can you see that we're taking up quite a bit of space listing out all of our possibilities? What I want you to notice, though, is that when we have a 2-topping pizza, it gives us 4 options, which is 2 to the second. When I have a 3-topping pizza, it gives me 8 options, which is the same as 2 to the third. When I have a 4-topping pizza, I have 16 options, which is 2 to the fourth. So I can see that my toppings end up being the exponent, 2 to the second, 2 to the third, 2 to the fourth. So in this problem, I'm going to use some inductive reasoning to say that the number of toppings, or number of possible pizzas, would be 2 to the 10th. So for this particular problem, we looked at solving a simpler problem first, and then we moved on to using inductive reasoning to find our solution. All right, we're going to try another problem. This time we're going to be looking at a snail that's trying to climb out of a well that is 30 feet deep. The information that we are given is that the snail can climb up 3 feet each day, and at night the snail slides back 2 feet. What day does the snail reach the top of the well? So for day 1, we have the snail here at 3 feet. But then overnight, he slides back so that he's really at the 1 foot mark the next morning. So then day 2, when he goes up 3 feet again, it's going to put him at 4 feet. So this here is going to be day 1, day 2. So then he's at 4 feet, and then overnight, he's going to slide back down 2 feet, putting him at the 2 foot mark. And the next day when he climbs up, he's going to be at 5 feet. So day 3. So at day 3, he's at the 5 foot mark. So I think we're at a good point here where we can go ahead and start to notice a pattern. We can see that right now we have a sequence of heights for each day. We have 3 feet, 4 feet, 5 feet, and it keeps going. We want to figure out when he's going to reach, when the snail's going to reach 30 feet. So this should remind us of what we were doing with sequences. It looks like the sequence we have here is increasing by 1 each time. We have the starting and we have the ending. And because it's increasing by 1, we know we're dealing with an arithmetic sequence. So we have a sub n is equal to a sub 1 plus n minus 1 times the d value. If we plug in the values that we have a sub n is equal to 3 plus n minus 1, and our constant difference was 1. When we simplify this, distributing that 1 through, we're going to get n plus 2 as our explicit formula. We want to figure out how many days, so that would be n, would it take to get to 30. So that's going to allow me to put 30 in for my a sub n. So 30 is equal to n plus 2, which means that my n value is 28. It'll take 28 days for that snail to get out of that well. So with this example, what we did was we first drew a picture of the situation here, or drew kind of like a chart. We ended up noticing a sequence, and from that sequence we wrote a formula to solve for the number of days. All right, we're going to look at just one more example. Meredith is buying some fruit, 25 pieces of fruit, apples and oranges. The total cost is $8.40. If an apple costs 24 cents and an orange costs 39 cents, how many of each did she buy? The method that's being suggested is guess and check. So one thing that we do know is that the total number of apples plus the total number of oranges should equal 25. So in using this guess and check, I'm going to just start picking out any arrangement of apples and oranges that add up to 25, and then I want to see if that total is equal to this $8.40. So if I start off with 10 apples and 15 oranges, I'm going to need to multiply 10 times 0.24 and add to that 15 times 0.39. And when I do that, I end up with $2.40 plus $5.85, and that gives me $8.25. I'm not at $8.40 yet. So what if I go 15 apples and 10 oranges? If I went 15 apples I'm going to take a look at 15 times 0.24. That's 360 plus the 390. That gives me 750. That's too low, so I might need to go back to the arrangement I had earlier. Let me try maybe 9 apples and 16 oranges and see where that gets me. 9 apples is going to give me 216, and 16 oranges is going to give me the 840 that I need. 16 oranges is 624, so that total is 840. So after a couple trials and errors, I can see that 9 apples and 16 oranges will give me the $8.40. So with this particular problem, we did look at the equation. We had two equations actually. One equation was the total number of pieces of fruit, and the second equation was the dollar amount. But we just tested out a couple of different possibilities to find our answer. Okay, the last thing I'd like for you to do is I have a link here to a video by a former high school teacher, Dan Meyer. He gives a TED Talk on problem solving. So please take a little bit of time and watch this video, and then go to Moodle and locate the Nearpod that has a couple questions regarding this particular video. Thanks.